Hello, class. This is Dynamics of Rigid Bodies, Lecture 3, Kinetics, Force and Acceleration. And this is just an additional sample problems to your existing ones. So this is going to be a problem walkthrough video, and hopefully you can pause the video and while you try to solve the problems yourself first. And if you're stuck and can't seem to figure it out, you may play out the video and see the step-by-step solution for yourself. Okay? Here we have sample problem 6. We have a baggage truck, A, so this one, and it has a weight of 900-pound force and tows about 2 carts, cart B and C weighing about 550 and 325 pounds respectively. Now, for a short time, there is the driving frictional force developed at the wheels of the truck is F of A, 40 T pound force, where T is in seconds. Okay, driving frictional force. I think the only reason why it's the frictional force is in this particular direction, I think that the truck here is just about to start. And whatever this force here is the amount of force that he has to overcome. I think. I could be wrong. Okay, so if the trucks start from rest, determine its speed in 2 seconds. Okay, so also, what is the horizontal force acting on the coupling between the truck and cart B in this instance? Neglect the size of the truck and carts. So yeah, going back to my initial analysis, I think when I was just reading it, why is the frictional force pointing to the left? Should it be in the right side of the equation? But then when I read it, it starts from rest. So maybe this is the amount of this is the frictional force that the truck must overcome. So we first solve this by engaging our imagination by drawing the free body diagram, of course. So we're going to go first for the case 1. So that is the determining the speed. And we have already a clue here, just like what I told you before. I think there's a pattern. Since we're finding speed here, we're going to be setting up our equations of motion first. And luckily, there's no vertical motion, only horizontal ones. So yeah. So before we go there, here's the FBD. You can draw it separately and simplify it accordingly. You don't need to draw the entire truck. Sometimes I just have enough time on my hands to draw them. As you can see, I'm not exactly drawing the tensions in between the couplings here because that is now being asked on the first case. That's the requirement for the second case. Okay. And then we now establish our equations of motion. And like I said earlier, luckily we don't have vertical motions here, only horizontal. And we plot it out. The equation of motion for x-axis should look something like this, and you'll be able to get the acceleration equals to 0.7250 t. Now, if you notice, why is 40 t positive here? So if we're going to follow our convention here, we could still arrive at the same thing. Since we could place negative here, and we would still arrive with a positive a. It just so happened the book, let me just put, if you're just following, if you're really reading it, the book has an indication saying that going to the left would be positive. If you check your books right now, it has this particular symbol. Okay? So in this particular case, our direction of the weight exerted by the cart and the truck would be positive as well, since, it's just a matter of perspective. But if we were to follow our usual convention, we would still arrive at the same answer of A equals to 7250. So what's our usual convention? Going to the right is positive. Oh, wait, let me just switch it up a bit. So different color so that for those of you who are would like to see the difference. Okay, there we go. And then let's choose a different color pen. So there we go. So in color, let's go with blue. So if we were to choose positive going to the right, that means going to the left is negative, we would still arrive at the same thing. So check it out. So here we would assume that the frictional force would be negative 40 T. And then of course, going down, our mass here, this is pointing at the downward direction. So we would assume it's going to be negative 900, negative 550, negative 325. So equals to We're just going to put it in this manner, negative 900 plus 550 plus 325. They're all going down. And then divided by 32. Oh, no. There we go. 174. A. The negative sign will still cancel out and we will still arrive at the same answer. Okay, so to those who already read this PDF file, hopefully you're not confused about that. Okay. So with that, now since we already set up since we already know our acceleration equals to 0.7250 t, we can now set up our kinematic equation. Recall our equation A. There we go. A dv over dt. Okay. So we're going to be using that, and then we're going to integrate both sides of the equation so that we will know our velocity at t equals 2 seconds. So it starts from rest, so our boundaries would be time is equals to 0. Time will be equal to 0. And then the second boundary would be time is equals to 2 seconds. So we will be using those boundaries to find our velocity. So let me just erase this since we have a presentation here. We have a certain animation lang. Okay. So you set out your kinematic equation. It would look something like this. So you isolate dv equals to a dt, and you integrate both sides starting from rest. So our initial point from our velocity will be 0. We're finding your final velocity. So integrating that will yield v. Here we will yield that will be t squared over 2. So 0.7250 divided by 2 will be equals to 0.3625 t squared. And we simply substitute t with these values, and we will yield 1.45 feet per second. Okay. So that will be the case 1. And for case 2, all we have to do is establish the FPD between the truck and the coupling, just like so. So it will look something like this. And then we set up our equations of motion. In this particular case, our only concerned motion will be on the horizontal side. So we have this one. Then again, the book follows its direction convention, where it declares that going to the left is positive. So the book has a convention. Wait lang. Let me just change the ink color to red again. So yeah, there we go. So it's positive. There we go. It's positive on the point to the left, and then positive going down, which is weird. Okay, so if you spread that out, the equation would look something like this. And then you will arrive with the answer of t equals 39.44 pound force. Now, if we use our convention, which is the one we already, which the one we normally use on our problems, you would still arrive at the same thing, because you would yield, t here would be positive, 40 times 2 here will be negative, then our 900 here will be negative. So it's something like, let me just change color. So we're going to use our convention. It's going to look something like this. It's going to be negative. This is going to be positive. This is going to be negative. And it still balances out. You will still get the answer of 39.44 pound force. Okay? Hopefully you're not confused as to why this 900 is being divided by 32.174, because 900 here is weight. All we did in the equation is mass. And weight is mass times acceleration due to gravity. So to get mass, you simply divide weight by the acceleration due to gravity. And since we're using FPS units, that's 32.174. Okay? So hopefully you got that, and I wasn't able to be confused there. So let me just erase all the ink here. So that's for problem number 6. Hopefully you had fun solving this. This is also present in your book, just in case you're much more comfortable reading a PDF rather than recording or my lecture PDF. Okay. Okay, next up is we have a spring. Okay, so let me just describe here. This spring here is moving in one motion. So it starts at point A, then it slides down at point C, stretching the spring attachment here. Okay, so just to not to confuse it, I tried to animate this honestly, but didn't have the patience to stitch the image together. So it starts at point A. Then this coupling is the same coupling here with the stretch spring. This one is the same spring as this one. Okay, so let me read the problem. Here we have a smooth 2 kilogram collar C, which is labeled C. This one is the same collar here. And to a spring having a stiffness of 3 Newton per meter. So this one has a stiffness of 3 Newton per meter. And an unstretched length of 0.75 meters. So this one, unstretched length at 0.75 meters. Now, if the collar is released from rest at point A, so here we are, determine its acceleration and the normal force of the rod of the collar at instant y is equals to 1 meter. Okay, so our starting point is this one. So you could say that this is our point origin, and it just dropped down at 1 meter. So that's gonna be negative 1 meter for sure. Okay, so let's just like how I do it before. You can start first with a given. I know lately I've been, doing some shortcuts, but just for lectures purpose sake, if you're having a hard time understanding what your givens are, you might as well write them down first before you establish your equations. Then write down then write down or draw your free body diagram. Then begin actually establishing your equations of motion or kinematic equations, and or vice versa. Okay, so in this case, it's gonna be like this. I should have included already that y equals to negative 1 meter, so that it's gonna be straightforward. So this is negative here, just to indicate that it's dropped. This is the reference line. So meaning anything here should be negative, so that's gonna be negative there. Okay. I wonder if I could increase the size of the pen. No, not much. Okay. Then what is our requirement here? We're here to determine the acceleration and of course the normal force of the rod. In this particular case, I'm just gonna call it normal force of R. Okay. So for our solution, we first have to establish our FBD. So we don't need FBD here. We would want the FBD representing the collar at point C. So here. So we have the weight of the collar. We know that if I'm gonna draw it straight here. So for example, this one, there's force of the spring here. There's the weight of the collar. Let's just and then of course there's the normal force here. There we go. So let's see if I'm right. So it's gonna look something like this. There we go. And of course the angle at which the spring is projected. And of course, don't forget that it's going down at a particular rate. So that will be our there's a change in speed here, or rather an acceleration or deceleration for this matter. Okay, so it's gonna be looking like this one. This one is important as well, so do not forget that. So I'm lacking that part, so there's a BA here going down. Okay. Several things we can actually get already. We can get theta since we have the unstretched length and we are given the total displacement of 1 meter going down. So we have that. That'll be 53.13 degrees. And then we can determine the spring force, which is simply F of S equals to K times S. And we substitute the known values here, where S here is the final length minus initial length. In this particular case, we can simply use trigonometry to determine the final length, because this is the final length, not 1. Okay, so we have here is 1 squared plus 0.75 squared minus 0.75. And we will have S at 0.5 meters. All we have to do is just substitute that. And then we can now establish our equations of motion. So in this particular case, we can start with the horizontal one. So we have f of x equals to m times ax. Luckily, in this particular scenario, there is no acceleration horizontally, so only vertical. So our ax here is technically 0. So we have something like this. So we have the summation, all we have here is the summation of forces in the horizontal. So we have here Fs cosine theta minus our perpendicular normal force. And then that will be our equation that we can actually solve now because we already determined the spring force and the angle. So our NR here is simply 3 times 0.5 and cosine 53.13, and your NR is 0.9 newtons. Next up is for the Y. We have summation of forces of under Y equals to mass times acceleration sub Y. So for the Y, we have Fs sine theta, and we have weight, which is minus m times g. We have m here, that will be 2, and then ay. So our ay is unknown here. So that's the one we need to know. Isolating I think we already have all our given here. Isolating everything, we will have the following. There we go. And ay is simply negative 9.21 meters per second squared. Now, if you think it's a little bit fast, you can always go back and review. So if you can see here, I just established the given, then establish my FPD. And with that, I think I just, hit the low-hanging fruits. Specifically, the angle, we can definitely determine that since we both have the your x and y values here. And we can determine that via trigonometry. So here we go. The Pythagorean theorem. And then with that, we can actually determine now your spring force. I just didn't substitute it directly. So I just inserted that in our equations of motion, just like so. And so again, 3 times 0.5, that's pretty much it. And then, of course, the angle here, 53.13 degrees. Forgive me. I think it's not necessarily to be negative 1 meter. So I have to erase that. Yeah, because if I'm going to use the negative 1 meter here, I will be using the other side of the angle, which corresponds to a different one. So since I use the angle in this manner, so the y here, I'm using y here as positive 1, and then the x here as 0.75. So hence, I arrive with a positive 53.13 degrees. That's fine as well. Don't worry about it. Okay. So let's just erase all the ink again. Okay, your y here is 1 meter, positive. Okay. Okay, next up is this one. This one is pretty simple, although we have a similar problem in our previous lecture, but this one, your force is represented by an equation. So here we have a motor M exerts a force of F equals 10d squared plus 100 newtons on the table. And where T here is in seconds, and T is time. Determine the velocity of the 25 kilogram crate when T is equals 4 seconds. The coefficient of static and kinetic friction between the crate and the plane are as follows, 0.3 and 0.25 respectively. The crate is initially at rest. So here, pretty much you have to establish first our FBD. So our FBD is something like this. You draw the box. We have our tension, weight, and then of course the normal force, and of course the friction. Okay, and then from there, we can now set up our equation of motion. So since we're finding the velocity here, so we're definitely going to set up our equations of motion first. We start first with the horizontal. I think that's what matters. So we have here, actually we can start with the y. So equal summation of forces along the y-axis equals the mass times acceleration. But fortunately, we don't have any movement or acceleration along the y-axis or vertical motion. So the other side of the equation will be 0. So instead, we will have only normal minus weight, which would equal to this. And substituting it would look like this. And we're able to solve NA, which equals to 245.17 newtons. Now we do the same thing for the x-axis. And there will be summation of forces along the x-axis equals to mass times acceleration. And luckily we have that. But we're able to substitute first on the x-axis only. It's going to be looking like this. It's going to be our force, or tension for that matter, minus the frictional force. And then equals m times a. And substituting all the values, we have this one. Okay, there we go. Notice I use the kinetic friction instead of the static. Why? Because we're going to move it anyway. The word here is the velocity is, so we're definitely going to use the kinetic friction here. And we will arrive with the equation of A equals to 0.4 t squared plus 1.483 meters per second squared. And with this, we can now set up our kinematics equation where we use again our formula A equals to dV over dt. And we isolate dV, and it will equal to like this. dV equals A dt. And we get to integrate both sides of the equation with dV as our limits here will be 0 to v. And then for the time sign, there will be 0 to 4 seconds. Should look like something like this. There we go. And then further establishing it, our V, further simplifying it, it would look like this. So that will be 2 over 15 t cubed plus 1.483 t. Yeah, that's pretty much it. And then substituting the 4 to the t, we'll have 14.7 meters per second. Okay. By the way, F here is also equal to t. This is the same. Okay, this one is the same. Just write different labels. If you want, you just replace it with F if you want. That's fine by me. Okay, or here, just replace it with T. That's fine by me as well. Okay, just make sure they're consistent. All right. Next up is a little bit of discussion before I present the problem for you guys. So this one is called, we have a concept called dependent motion analysis, which usually involves with pulleys and cables. Okay, so I understand back in statics, we're only concerned of the tensions involved. We're not exactly looking for the cord length or for anything like that. So just in summary lang here, notice the highlighted cables here in red. They're usually constant in length here, and just for simplicity's sake, we don't usually take them into account. What we do take into account is the changes. So for example, here, S and B, that will be consistent. And what else? And that will be the H. Okay. So I think SB and SA are the ones who's changing here. Okay. So the system's geometry links the motion of interconnected blocks hanging the pulleys and cables. To execute and find the cord length here, one must define the position coordinates of each block, just like so. So the displacement between point B and its datum line against the datum line, and then of course the datum of from one pulley to point A, which are measured from a fixed point and aligned with the block's direction of motion as represented as such. So for this particular graph, it's going to be 2SBY because there's 2 legs here. So this is the cable length here, this particular side. And then this one, so that will be SB plus SB, that will be 2SB plus H plus whatever the length of SA, that will be your total cable length or length. Now, if you recall, if you're gonna ask, hey, sir, what happened? Why did the S become the V and then V became A? If you recall, A, to get A, simply get the first derivative of velocity or the double derivative of displacement. So in this case, we just derive it twice. You can derive twice the displacement, and you arrive with A with acceleration. So by deriving this equation, one can understand how the velocity of the blocks are interconnected. Here we go. So this will be 0, 0, and you're left with VA 0. The next one, if you integrate this further, additionally deriving a second derivative reveals the relationship between their acceleration. So in this case, from this perspective, it's gonna be one derivative for just one derivation lang. Pero from the perspective of displacement, it's gonna be two derivatives. So that will be 2AB and A. And don't worry about the dt because the dt will cancel out eventually. Yeah, you can actually divide both sides by dt, and you'll have this particular equation. And just a word of warning lang here, the total cable length varies depending on pulley cable layout. So this particular formula is not standard. So you have to depend this equation on what the layout is. So this one is true only for this particular layout. Okay? And you would know why. So let's try it out with this one.